Today's program is going to discuss, obviously, the 2015 Special Design Provisions for Wind and Seismic. I'm going to assume that most of you all took a look at the description as well as the learning objectives when you signed up, so I won't spend too much time on these. We'll be talking about some lateral load basics for the first portion of the program, and then after that we'll get into some kind of code and standard heavy material. So most of you probably have designed many shear walls, many structures for lateral loads, but I do like to start with some of the basic terminology just so that everybody's using the same terms and kind of on the same page, as it were. So if we think of our two main sources of lateral loads, those are wind and seismic, as you could probably guess by the title of the document, that Special Design Provisions for Wind and Seismic. In the IBC, section 1604.4 requires a complete load path. So how we accomplish that complete load path is obviously going to be dependent upon the materials, the geometry of the structure, many, many different elements. But the special design provisions for wind and seismic serve to provide a framework for development of a complete lateral resisting load path for a wood frame structure. So we're going to talk about wind first, just because that's the order the slides are in. But if we look at a wind load being applied to a structure, so if we take a look at grab my arrow, there we go. So if we take a look, and assuming that the wind is blowing in this direction into this gable end of this little house we've got represented here, we assume that the diaphragm is supporting the out-of-plane walls in this instance. So that means the walls that are running kind of in this left to right direction, if you will. The in-plane walls are what are supporting the diaphragm. So that would be the walls that are oriented parallel to the direction of the wind. And obviously, we have windward pressures, and typically we develop suction on the leeward side of the structure. This is just another illustration of our lateral load path. Again, our horizontal diaphragm for a roof, for example, would carry that load to the end walls that are supporting it. The side walls are going to carry the load. Half of it would be carried to the top of the wall, to the roof diaphragm at the top of the wall, and then the bottom half of the wall we would consider to dump that load directly to the foundation. And then our end wall, again, is carrying, our end wall would be our shear wall. You may sometimes hear them referred to as vertical diaphragms. I'm not a huge fan of that term, but it's certainly not an incorrect statement to refer to a shear wall as a vertical diaphragm. And indeed, when you start looking at the designs of shear walls and diaphragms, they do have many similarities. So it's not necessarily that much more difficult to design one compared to another, or to the other. So if we think of our diaphragm as a deep beam that is supporting a distributed load, we have our distributed load being applied in this example. It would be a wind force, but it certainly could also be a seismic force. And we have the chords at the top and bottom of our beam, these that would be assumed to carry the compression and the tension depending on the way that the load is being applied. And then the reaction of that deep beam that is resisted by the diaphragm, is resisted by the shear walls. So the diaphragm reaction then is carried into those supporting shear walls that we talked about a couple of slides back. When we talk about seismic designs, and when I talk about seismic designs, we're typically going to be talking seismic design categories C, D, E, and F. The seismic design, again, it's still designed as a deep beam, but we have a few provisions for seismic design in ASCE 7 that are slightly different than some of the wind-only provisions.